Number 60. Calculate the concentration of all solute species in each of the following solutions of acids or bases. Assume that the ionization of water can be neglected and show that the change in the initial concentrations can also be neglected. Okay, and then last one out of the bunch. So we have letter E, so 0.120 molarity of FeH2O6 2+, which they told us was a weak acid, and they give us the Ka value, 1.6 times 10 to the negative 7th. Cool. Okay, so the first thing is that they want us to find all concentrations, and when they're saying that, what they're saying is they want us to find the equilibrium concentrations. Because we only started with initial concentrations, 0.120 molarity. Molarity is another word for concentration. That's saying that we initially started with 0.120 molarity of FeH2O6 2+, then we got to find out all the equilibrium concentrations. So when we're trying to find out equilibrium, we're starting with the initials. We need to do an ice table. But the first thing is we got to write a balanced equation. So this is saying that it's a weak acid. So there's a little trick with weak acids. This one is going to kind of be tricky though, but I know you guys can do it. So what I'm going to do is I'm going to say, okay, we got Fe, H2O, 6, and then 2+. Now, generally speaking, with acids, so for example, like HCN is an acid, right? You can do this trick where you can just disassociate the acidic H from the rest of the components, and it would just be H plus CN minus. But here, it's a little bit hard because I have these hydrogens attached to, the waters. But if we think about it, let's see. I know that this is a weak acid. They told me that, so it's going to be disassociated, right, into equilibrium. And I know that by definition, a weak acid has to give off one H+. So that's without fail. But now the hard part is figuring out what is going on here. How am I going to write this out? Well, keep in mind that you have 6 H2Os. So here's 1, here's 2, here's 3, here's 4, here's 5, and here's 6. Remember, you're just losing one hydrogen out of these 6 H2Os. So maybe I'll talk about the last one. And when you lose a hydrogen, this just becomes HO. But we don't write it like that. Ho, ho, ho. We write it as OH, right? OH minus is hydroxide. So how many H2Os do you have left? You have 5 left. 1, 2, 3, 4, 5. So I'm going to say I have Fe, H2O, but now I have 5 of them and the remaining OH. So maybe I'll just put that in parentheses just to kind of, put it away from the H2Os. You don't have to put it in parentheses. You could just say OH, but I think the parentheses looks better. And now, if you removed a hydrogen, you drop 1. So 2 minus 1 is just a plus 1. So I'll just say plus. And now that is my balanced equation. So I'm going to put this over here. Now we know that we have to use an ice table. So let's ice it up. Ice, ice, baby. Does anybody know who that is? Ice, ice, baby. Best thing in the world when he said he didn't copy Queen. How dare you? Anyway. Okay. Okay, so here we go. ICE. I stands for initial, right? So initial concentrations. They only gave you one value, 0.120 molarity, and that was hooked up with the FeH2O6 2+. So that 0.120 has to go here. Now, did they say that I started off with H plus or FeH2O5OH? No. So I have to assume that I don't start off with any of those, so 0 and 0. C stands for change. How much this value dropped and how much these went up, right? Remember, you can't go lower than nothing, right? You can never have negative molarity. So if you started with 0, you always got to go up from there. So this would be plus, and this would be minus. Now, how much change? I don't know. So that's why we put in a variable. A, B, C, D, E, F, G. Let's do the alphabet. Pick any letter, but we always pick X, right? So this would be minus X, and plus X. And with acid-base reactions, your coefficients are always going to be a 1 to 1 to 1. So you don't have to worry about like minus 2x or plus 3x. So thank goodness for that. E stands for equilibrium. This is where you're going to pull your initial and your change together. So 0.120 minus x is 0.120 minus x. 0 plus x is just x. 0 plus x is just x. Now we're ready to go. We input our equilibrium line into our Ka formula. And remember, from the equilibrium chapter, Ka equals products divided by reactants. Anytime that you see charged ions, those are always going to be aqueous. So by default, this is aqueous, this is aqueous, and this is aqueous. They're all going to be included in the Ka formula. So let's just write that out for now. Ka equals, this one's going to be pretty long. So we have the H plus, we have that huge thing divided by the reactants, right? Products minus reactants. And remember, the two products are being multiplied by each other. So this would be Fe H2O 5 OH plus, and then this would be Fe H2O 6 2 plus. Now, they do so that we have to show the change in initial concentrations can be neglected. This is the only one in which you had an initial concentration, and C stands for change. Now, since this Ka value is so small, it's times 10 to the negative 7th. That means that at equilibrium, you're going to favor your reactants. But if you started with reactants and you're going to end with mostly reactants, is this minus X really going to be a big number? No, it's going to be so small that we don't even care about it when it comes to math. So for math purposes, we can get rid of this because that X won't make a difference as to what the answer should be. When we actually come back and find the equilibrium, then we're going to actually minus X, whatever the X we find. So now let's just plug in our values. Ka, they told us, was 1.6 times 10 to the negative 7th equals something divided by something else. We got the two values up top. We got the 1 on the bottom. X times X. We're only taking equilibrium values, and 0.120. We can cross multiply, right? The 1.6 times 10 to the negative 7th times the 0.120. Maybe I'll bring this up a little bit. X times X is X squared. And then let's see what we get. 1.6 times 10 to the negative 7th times 0.12. So I'm not going to round just yet because that's not my final answer. 1.92 times 10 to the negative 8th. Take the square root because we just want to find out what X is. And maybe I have room down below. X equals square root of that. And now I'm going to cut it off at 3 sig figs, I guess, because this is technically a constant value. So we're going to go by this value if anybody cares about sig figs. So we'll say 1.39 times 10 to the negative 4th. And those are your X values. X equals that. So the concentration of H plus or H3O plus, it means the same thing, is X. And so is this big guy over here, right? So we have H plus hydronium being equal to 1.39 times 10 to the negative 4th molarity. Same thing with Fe H2O 5 OH plus 1.39 times 10 to the negative fourth molarity. So these are accounted for. Now when we do this math, we have to do 0.120 minus the 1.39 times 10 to the negative fourth. Just to see how much it's going to change, but it's not going to change that much. 0.12 minus 1.39 times 10 to the negative fourth. And if we just drag out that number a little bit, Fe H2O 6 2 plus concentration is 0.1199 if we round. So as you can see, you started off with 0.12 and you're ending at like 0.1, basically 1.2 if you rounded. So that gets rid of this one. But now here's the catch, guys. It says we need to find all solute species. And if you have an H plus concentration, you secretly have an OH minus concentration. That's down here. If you have H plus, you have to convert to OH minus. So what I'm going to do is I'm just going to drag this out, because now we're going to use this formula. And maybe I'll get rid of this. So if we have H plus, we want to solve for OH minus. What we would do is we would divide on both sides by H plus to get rid of that, right? So that's what I'm going to do now, just to make this the simplicity of the video. I'm just going to divide by the H plus concentration, and that will give you the OH minus. The H plus, we just found out to be 1.39. That was the X value, times 10 to the negative fourth. And then the KW value is always a constant value. Your teacher or professor probably wants you to memorize this. It's 1.0 times 10 to the negative 14th, or just 1, or 10 to the negative 14th. Doesn't matter to me. So let's do this math. This divided by this equals the OH minus concentration, which I'll put up here. 1.0 times 10 to the negative 14th divided by 1.39 times 10 to the negative fourth. And now my OH minus concentration, add that to the list. 1 times 10 to the negative 14th divided by 1.39 times 10 to the negative fourth. I get 7.19 times 10 to the negative 11th molarity. And since I have way much more hydronium than hydroxide, this is clearly an acid. So you can kind of check your work. And that's it. These are all of your answers for species in, this equation. And that's it. I really hope this helped. This is the end of number 60. Thank goodness. So if you wouldn't mind, please press the subscribe button. Just gets the word out there in the YouTube universe that this cool channel exists. Thank you so much for that. Channel wouldn't be where it is without you guys, so your future is in our hands. Thank you. I will see you all in later lessons. Have an awesome day. Bye-bye.